In the last story, Profil raced through your prompt and produced the very first token. But then what? The answer keeps streaming, word after word, and for a long reply, that streaming is where most of your waiting actually happens. This is decode, and decode has a very different bottleneck than Profil. Decode is how a language model writes. It is autoregressive, which means it generates one token at a time. It produces a word, appends it to the sequence, and feeds the whole thing back in to produce the next word. Each new token depends on every token before it. So unlike reading, writing cannot be done all at once. It is fundamentally sequential. And here is the catch. To produce just one token, the model runs a complete forward pass through every single layer. Billions of parameters activated to generate one word. Then it does it all again for the next word, and the next. A 500 token answer means 500 full passes through the network, strictly one after another. So what is decode latency? It is the time between tokens, often called inter-token latency or time per output token. Your total generation time is simple, the time to first token plus the number of output tokens times the latency of each one. Profil is paid once, decode is paid on every token. For long answers, decode dominates the clock. Now for the surprising part. You might think a bigger, faster chip with more raw compute would fix this, but decode is usually not limited by compute at all. The arithmetic per token is tiny. What actually slows it down is something else entirely, memory bandwidth. Decode is memory bound. Think about what one decode step requires. To compute a single token, the GPU must read every weight in the model out of its memory, billions of numbers, just to use each one once. The calculations finish in a flash, but moving all that data takes time. The work is small, the data movement is enormous. That is low arithmetic intensity. This is the memory wall. The compute units, the part everyone brags about, sit mostly idle, waiting for weights to arrive from memory. Adding more raw compute does not help because the chip is starving for data, not for math. To make decode faster, you have to move fewer bytes or move them more cleverly. That reframes everything. The first factor is model size. A bigger model has more weights, which means more bytes to stream from memory for every single token. Double the parameters and you roughly double the memory traffic per token. Larger models do not just cost more to train, they decode more slowly. The second factor is the KV cache. Remember, every token attends back over the entire conversation, so the model must also read the growing cache of past keys and values at each step. The longer your context, the bigger that read. As a chat gets longer, each new token quietly gets more expensive to produce. The third factor is how many requests share the GPU. When you generate for just one user, you stream all those weights to produce a handful of tokens, wasting most of the chip's bandwidth. Decode at batch size 1 is the least efficient thing a GPU can do. Utilization, it turns out, is everything. So how do we fight back? The most direct win is quantization. If decode is bottlenecked on bytes, shrink the bytes. Store the weights in lower precision, 16 bits down to 8 or even 4. Fewer bits per weight means far less data to move each step. For a memory-bound workload, that translates almost directly into faster tokens. The cleverest trick is speculative decoding. A small, fast draft model guesses the next several tokens. Then the big model checks all of those guesses in a single forward pass, the same pass that would have produced just one token. Every guess it accepts is a token you got almost for free. When the draft is good, this can double or triple your speed. Next, shrink the cache itself. In standard attention, every head keeps its own keys and values. Grouped query and multi-query attention let many heads share one set instead. That makes the KV cache far smaller, so there is less to read every step and longer contexts stay fast. Most modern models now ship this way. Then there is continuous batching. Instead of making requests wait in line, the server continuously packs many of them together, so a single read of the weights produces tokens for dozens of users at once. It turns wasted bandwidth into throughput, the same memory traffic suddenly serving a crowd instead of a single person. And the work keeps going. FlashDecoding restructures attention to stay fast even over very long contexts. Smarter sampling and parallel hardware help too. And of course, chips with higher memory bandwidth attack the bottleneck directly, since for decode, bandwidth, not raw compute, is the number that matters most. So remember the second half of the story. Decode writes the answer one token at a time, each token a full pass through the model, and it is bound by memory bandwidth, not compute. Total time is Profil plus tokens times their latency. To speed it up, shrink the bytes, skip steps, and share the work. Master both phases, and nothing about the model feels slow.